In section 2.5, we're going to talk about the fundamental theorem of algebra. Our objectives here are to use the fundamental theorem to determine the number of zeros of a polynomial, find all zeros of a polynomial, so all zeros will include real and imaginary, find conjugate pairs of complex zeros, and then find zeros of polynomials by factoring. So the fundamental theorem of algebra says that if a polynomial of degree n, so if you have a polynomial that has the degree n where n is greater than 0, then there is at least one zero in the complex number system. So it has to have a 0, whether it's real or imaginary, it has to have a 0. So using the fundamental theorem and then the equivalent of zeros and factors, you can obtain your linear factorization. So what that says is any polynomial can be factored into linear factors. So linear factors means that the degree of each factor is 1. So you would have x plus or minus something for each term, and then you would have some sort of constant out front. So this kind of note here that neither the fundamental theorem nor the linear factorization theorem tells you how to find the zeros. It just tells you that you have zeros and that you can write them as linear factors. So to find the zeros, you have to rely on other techniques. So in this first example, we have a first degree polynomial, x minus 2, has exactly 1 0 at x equals 2. It has a degree 1, and if you set x minus 2 equal to 0 and you solve for x, you get that x equals 2 as the 0. If we were to talk about multiplicity, we know that x squared could potentially has 2 zeros, and if we were to factor x squared minus 6x plus 9, it would factor into x minus 3 and x minus 3. So we know that your function has 2 zeros at x equals 3 because you could set your factors equal to 0 and then solve for x. And so since it has 2 zeros, it's a repeated 0, or we would say that this one would have the multiplicity of 2, which means it would just touch at 3 and then go back. It's not going to cross the x-axis at 3. So we have a third degree polynomial in part C, and here if you factored out the x, you're left with x squared plus 4. And x squared plus 4 actually factors into x minus 2i and x plus 2i. And if you don't know that off the top of your head, again, what we can do is say x squared plus 4 equals 0, set it equal to 0. And if we're solving for x, we would have x squared equals negative 4. So if we took the square root of both sides, we would get plus or minus square root of negative 4. So that's where x would equal plus or minus 2i. Right, and if x equals plus or minus 2i, then if we were to write it as factors, this would be how you would factor it with linear factors. And your zeros would be 0, 2i, and negative 2i. If we look at D, again, factor out that GCF. So we have 3 zeros at 0, right? So 0 would have a multiplicity of 3. And then if we have x squared plus 9, if you remember the pattern from here, right, that's going to factor into x minus 3i, x plus 3i, so then you also have those as your other zeros. So that will have exactly 5 zeros. Remember that the n zeros of a polynomial can be real or imaginary, and they can also be repeated. So if we need to confirm that the third degree polynomial of x cubed plus 4x has exactly 3 zeros, then what we would do is if they gave us the zeros and we had to confirm that those zeros resulted in this polynomial, what we're going to do is put them as factors. So we would have x, and then if we took this and wrote it as a factor, we would have x minus 2i, and the next one we would have x plus 2i, and then we would FOIL those out. So if we start by FOILing these first two parts, we would have x, we would have x squared plus 2xi minus 2xi minus 4i squared, which really gives us x squared. The plus and minus 2xi simplify, and minus 4i squared is plus 4. And then if you were to distribute that x in, you would get the f of x equals x cubed plus 4x. So if you were given the zeros, you could confirm that it indeed does have a certain polynomial that goes with those zeros. So whenever you have a polynomial that has real coefficients, if it has a complex zero or an imaginary zero, so if you have a zero at a plus bi, it will always have its conjugate zero, which would be a minus bi. Because by multiplying those conjugates together, that's how we get rid of that imaginary part, and it only looks like we have those real zeros. Be sure you see that this result is true only when the polynomial function has real coefficients. So it would work if we had x squared plus 1, but if our polynomial was x minus I, where we don't have all real coefficients, then that rule doesn't hold. So in this next example, let's find a polynomial with the given zeros. So we need a 4th degree polynomial, and we have zeros at -1, so x equals -1, another one at x equals -1, and then we have x equals 3i. And because we have a polynomial with real coefficients, we also have to use the conjugate, so -3i. And so now what we're going to do is write this as factors. So x minus 1 as a factor becomes x plus 1. The other x equals -1 will become another x plus 1. And then here, if we write those as factors, we would have x minus 3i and x plus 3i. So when we're doing this type of problem, if you're asked to find a polynomial with real coefficients, what the expectation is that once your factors have real coefficients, you don't need to continue to multiply those out. But when you have these factors with complex coefficients or imaginary, we're going to need to multiply those parts out, so that way everything that we have is real. So we're going to leave the x plus 1, which will probably condense to an x plus 1 squared here in a minute. But when we FOIL out this x minus 3i and x plus 3i, we get x squared. You get plus 3xi minus 3xi minus 9i squared. So again, if we continue to simplify, we get x plus 1. We'll write that as just the quantity squared, combining both of those factors. And then we have x squared plus 9. And then we're just going to leave it. I don't need you to keep multiplying it out. At that point, everything has a real coefficient, so knowing that you could potentially multiply it more, you'll still have real coefficients. So now when you have to factor a polynomial, remember the linear factorization theorem says that you can write a polynomial as the product of linear factors. But what that means is that some of those factors could potentially have imaginary zeros, or you'll have what would be called like an imaginary factor. So every polynomial of degree n greater than 0 with real coefficients can be written as a product of linear and quadratic factors with real coefficients, where the quadratic factors have 0 solutions. So if you need all real coefficients, you may still have some quadratics left. A quadratic factor with no real zeros is said to be prime or irreducible over the reals. So if you had like a quadratic left that was x squared plus 1, if they said to factor over the reals, we would leave it in this form. But if it said to factor completely over complex, then we would need to factor it down into this form. Where if you had a quadratic that was x squared minus 2, you could actually still factor it over reals. They wouldn't be rational numbers, they would be irrational, but root 2 and negative root 2 are still real numbers. So for this example, we're going to first write the polynomial as a product of factors that are irreducible over reals. So something that could be a little bit tricky, when you have this x to the 4th and x squared, we're still going to treat it in a way of factoring it like we would like if this said x squared minus x minus 20. But instead of it factoring into an x times an x, it's going to factor into an x squared and an x squared. So that way that first term when you multiply is x to the fourth, but that middle term is still x squared. And then you have to think about what multiplies to give you 20 and adds to give you -1. So we're going to go -5 and +4. And so we still need to be able to factor. Now this factor right here, x squared plus 4 doesn't have any more real zeros. But x squared minus 5, if we factored it as a difference of squares, would factor into x plus root 5 times x minus root 5. And then we'd write times x squared plus 4. Because we want it to be factors that are irreducible over the rationals. So as a product of linear factors and quadratic factors that are irreducible over reals. Oh, so that was actually this part. So I guess what we're going to do is take this whole group right here and we're going to move that. So we're going to say x plus root 5, x minus root 5, and then x squared plus 4 is actually going to go down here. I didn't read this top part very carefully because it said over rationals, and rationals are not root 5 and -root 5. So what that means then is that for this first part A, we're not going to have this line in here. That just this part, x squared minus 5 and x squared plus 4, anything beyond that won't be rational. So the key there was rational. And then the last one in C is completely factored. So that means completely factored means all linear factors. So you already have 2 in the x plus root 5 and x minus root 5. But now you need to factor x squared plus 4. So remember that you're figuring out where does x squared plus 4 equal 0 if you were finding the zeros. You can factor it as a sum of squares if you remember that pattern. But if you don't, then again, just solve your equation and you get x equals plus or minus 2i. So your other factors are x plus 2i and x minus 2i. So when you're factoring a polynomial, the results and theorems that have been stated in terms of zeros of polynomial functions. So make sure that you see the same results could have been stated in terms of solutions of polynomial equations, and that's because the zeros of a polynomial function are the same as the solutions of a polynomial equation. So it's just a different way to say something. So if they ask you for the zeros of a function, it's because they've kept that function notation in. If they ask you for the solutions, they've changed that function notation and set it equal to 0, so that way you're finding the solutions. So in example 7, we're going to find the zeros of the polynomial x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60. So these have all real coefficients. And the only information is that x 1 plus 3, x equals 1 plus 3i is a 0, which then means that if we have all real coefficients, that the conjugate also has to be a 0. So if we were to write these as factors, and we move the 1 and the 3i over, we would have x minus 1 minus 3i. Same thing here, if we move the 1 and the 3i, we would have x minus 1, it's an x. We would have x minus 1 plus 3i. So what we're going to do now is FOIL this out. FOIL this out, we get x squared minus x plus 3xi. And now I always put my things vertically where they fall. So minus x, so I'm going to put that under my x, plus 1 minus 3i. So I always group my like terms. And then I have minus 3xi plus 3i minus 9i squared, which is the same thing as saying plus 9. So when I look to combine these, the 3xi, negative 3xi, negative 3i, 3i. So now I know that x squared minus 2x plus 10, right? Because I have the x squared, I have minus 2x, and then plus 10 is a 0, or is a factor of that polynomial. And so if that's a factor, And I need to find all the zeros. So again, I already have this first zero they told me. I have the second one using that conjugate zero rule, but there's still two more zeros. So what I'm going to do is once I have that x squared minus 2x plus 10, I'm going to use long division and find my other factor. So what multiplies x squared to get x to the fourth? I'd say x squared, so I'll have x to the fourth minus 2x cubed plus 10x squared. When I subtract, I get negative x cubed minus 4x squared plus 2x minus 60, bringing down that 2x and the 60. So then I would say minus x is what I have to multiply by, and I get minus x cubed minus plus 2x squared minus 10x, subtract. So then I get minus 6x squared plus 12x minus 60. And that means I have to multiply by negative 6. And if I do that, I get negative 6x squared plus 12x minus 60. So when I subtract, I get that remainder of 0. So my other quadratic factor is x squared minus x minus 6, which I could factor into x minus 3, x plus 2. And if I want to find the zeros and set each of those factors equal to 0, I would get that x equals positive 3 and negative 2 are my other zeros. So those would be my real zeros. And up here, these would be my other two complex zeros.